Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am very happy to have Pushpak Pandey with us today. Hello, Pushpak.
Hi. Hi.
Pushpak. I got to get the extra P in there.
Yeah,
Very cool. How you doing today?
it's a good day. I mean, it was a slow day also. So yeah.
Very cool.
Yeah.
And Pushpak, what's your geolocation? Where are you located at?
So I am here at Ayuka, Pune in India.
Cool.
So
We are going halfway around the world on this one.
yeah. So it's yeah.
Very good. And
And
go ahead.
I'll say yeah. So the altitude is like 500 feet. I was going to say that, but I thought, okay, not this information.
Okay, very good. And it is February
Yeah.
18th of 2025 as we record this. And I am in Phoenix and I'm in the desert and
Yeah.
definitely warming up into spring. Is spring coming around in Pune?
Yeah.
Yeah.
I don't know if you call 30 degrees Celsius spring, then maybe. But
I will, I
mm,
will. I'll call it that. Very cool.
usually there is no winter. Winter is probably the good time
Ooh, yes.
for us. It
Little,
usually goes from winter to summer. Yeah.
yeah, no transition. Very much
Yeah.
a few places. Very cool. And pushback, what do you like to do for research?
I work in, okay, so the article that we're trying, we will be like, discussing today is a method. It's a method paper, but yeah, usually I do observational
Okay.
astronomy, basically galaxies. I observe ultraviolet emission from galaxies, extreme ultraviolet emission from disk galaxies, that the
Cool.
XUV disks you might be aware of. So I am trying to look at galaxies in the intermediate redshift right now.
Awesome.
So which has not been done, and yeah, so that is what constitutes majority of my research.
Right.
Yeah. So this is a byproduct of that.
Very
This
cool.
article will be about.
Very cool. And that is going to bring us to this very awesome APJ supplement article. It is open access. It's the open access era, people. You can go grab a copy for free. A geometric approach to estimate background in astronomical images and pushback. Take us away.
Yeah. So before going through the paper, I would like to discuss like how we started with this.
Okay.
Is that usually when you take astronomy image, processed astronomy image, you need to do background subtraction, and you need to do an RMS estimate pixel by pixel of that. So that when you uh, take the flux of an object, and yeah, you need to subtract that particular background to
Okay.
get the correct estimate of that flux. But usually what happens is people use some automated softwares like source extractor. I mean, it's a very good software.
Huh?
It's a very good software for very large surveys and all. But but what it does is it looks at the image by collapsing the pixels into a 1D histogram, and
Okay.
it tries to do a sigma clipping there, and like tries to get a mode from those points, and assigns that value to the patch of the sky where it is doing that particular operation,
I'm with you.
and that would be the background of that particular patch. But usually what happens, if there is a very bright source there, or if the source coverage is very large, then you will end up overestimating the background.
Okay.
So,
Okay.
yeah, and when we so basically, when you look at very noisy images and you want to get the most out of that image, you know that there is a source, but if you run source extractor, it may overestimate, or it may give you a very bad background value, because source extractor only works on the Gaussian limit
Okay.
of the Poisson, because the random variable is basically the pixels are all Poissonian, right? I
Right.
mean, when you get an image, you look at the pixel distribution. If it is not altered, very much, if it is not, so the pixel distribution will be a perfectly Poissonian
Okay.
because it's a Poissonian process. The
Uh-huh.
photon counting is a Poissonian process.
Uh-huh.
So when you look at a very, suppose a very noisy image in the and that is in the Poissonian regime, and suppose that exposure time is very low, and you're looking at many zeros, many like very few pixels are enlightened, and there is just one bright source somewhere there. And
Okay.
how are you going to do the background? If you do source extractor, the mode is zero.
Yes. Okay.
So, but that is not the background rate. I mean, if you're working on a very noisy regime, there very low lambda. uh, when I'm saying lambda, lambda is basically the mean background value into the t exposure time,
Okay.
exposure time.
Okay.
Okay, so when you're looking at very low lambda values, the mode is always zero, the median is always zero. So
Yeah.
yeah, so if you use these older methods and it's these available methods, then you end up with a bad background estimate.
Yes.
And if you, I mean, you need a very balanced background estimate. So what usually people do is they put boxes by hand around an object. If they're working on one simple object, they'll put boxes around it.
Yes.
Wherever they see like there is no source there, and they'll take an estimate and they'll try to put it as randomly as possible. When we were working, well, Kanak, it started with Kanak because Kanak had a set of data in the Good South. Yeah,
Mm-hmm.
Kanak is my co-author. So, yeah.
Good.
So Kanak had an observation in the Good South, and he was, I think, working on his first paper from this,
Okay.
which is a Lyman continuum source at 1 point some redshift in that redshift region.
Yeah.
And yeah, so it's a very faint source, and you need a very careful background estimation, because if
Okay.
you do a automated background, it will wash it out.
Okay.
It's just reaching, like it's 3 SNR source. It's almost a 3 SNR source, and
Okay.
3 SNR source is very easy to uh, pass by, and you may not notice it unless you are very careful.
Okay.
So usually, yeah. So in that, yeah. So usually, what people did was, they put boxes around, but you can only do this for single objects.
Okay.
Yeah. So yeah. So basically, we wanted to look at a possibility, because he wanted to convert that whole observation into a catalog,
Mm-hmm.
UVIT catalog. The UVIT is the instrument, which is based on which is on Astrosat, which is an Indian satellite,
Yes.
and UVIT observes in NUV like 242 and F, or I think 154 nanometers and so on.
Yeah. Okay.
It's the two bands which are most popular. So yeah, we had these two images and we wanted to do a background, but yeah, he wanted to get the most out of it. And source extractor in the FUV image was doing the same thing, because the FUV
Yeah.
image, even at like 60 kiloseconds,
Okay.
had a lot of zeros.
Okay.
And if you do a mode or median estimation there, it's a zero. So background is not there. I
Okay.
mean,
That's a
you can
problem.
put boxes by hand all around the image
Yes.
and do it probably, but yeah, that takes a lot of time. So he
Got it.
thought that, can we do
A better job.
like yeah, better job, like can we make this placement of boxes automated, and where we do not yeah, without the knowledge that if there is without the knowledge that if there is source there or not,
Right.
how can we put boxes at places where there is a high probability that it is source free,
Okay.
like you do by hands.
Okay.
So yeah, so that is what pushed this project forward. And the first idea was to look at smoothed image, the minima points of the smoothed image,
Ah, okay.
basically.
Yes.
So if you put boxes there at minima, because minimas are less likely to have sources there.
Okay.
So that was the idea where it started from.
Cool.
And yeah, so yeah, there are some other methods. I mean, I have discussed it in the introduction also. You can see. I think somewhere, can you go a little bit below?
A little farther down, sure. So,
Yeah.
got our intro, then we get into the minima statistics part.
No, in the intro only.
Okay.
Okay. Yeah. So you would see, yeah. So I have cited Mark Rafalski and Chayan Mondal, Kanaksa et al. Yeah,
Okay.
in this particular paragraph also. So yeah, so one method. Suppose you are in the Gaussian regime and you want to avoid sources and you want to use source extractor. So what do you want to do? You don't want to do overestimated background. The one thing you can do is you can run source extractor,
Yes.
mask out the sources, and then iterate the process all
Right.
over again.
Uh-huh.
Yeah, mask the sources, run source extractor again, and it will go somewhere near the mode, and like yeah, you can get a better background estimate. But then again, if there are very faint sources, then you'll miss them. I
Right.
mean, this is what we observed with UV8, the observation that we had. So before starting this project, so yeah, so basically this project, so before starting this project, what I wanted to know was if we just choose minima,
Okay.
does this bias our estimate in
Yes.
general?
Okay.
Because you are looking because okay, so you some like one argument that came during this discussion in our group was I'm choosing these minima pixels, but these minima pixels belong to the same probability distribution which other pixels belong to. So why would the distribution be same? But yeah, but the counter argument is that you're choosing the minima pixels based on some criteria.
Yes.
So the criteria is basically its nearest neighbors would be bigger than this, right? And
Okay. Okay. I'm
if
with you.
it's yeah,
Uh-huh.
so if suppose you take a 2D array filled with random variables and
Okay.
you select minimas and you yeah, and just select what do you mean by selecting minimas? You choose the pixels whose nearest neighbors are higher than that particular pixels
Yes.
have
Identified it.
have higher values. So that has to come into the probability distribution of these minima pixels.
Okay.
So if I run it, I mean that whole 2D array is based on suppose a single mean and sigma normal. It's a normal distribution. I mean it's filled with random variable from the normal distribution with a mean and a sigma.
Okay.
And if we just choose the minima pixels, the mean of those minima pixels will be lower than that. But turns out that this particular bias
Okay.
can be analytically shown and
Okay.
it can be calculated easily. And we
Nice.
can go below.
Mm-hmm. Okay.
Uh,
Minimum in its parent probability distribution.
yeah, so that's what I was discussing. Yeah, so you can look at the equation one.
Okay.
So yeah, so this is so suppose so what is the probability distribution of those minima pixels? So first of all, if I'm choosing a pixel, then what is the probability that the pixel has a value x? And what is the probability that the nearest neighbors
Yes.
have a value higher than x?
Okay.
So these two, so these two, these two factors are basically the main parent probability distribution from which the minimas are calculated, which
Yeah.
is the px, and the choice that the nearest neighbors are higher than that is
Yes.
shown by the 1 minus phi x to the power n. N small n is the number of nearest neighbors.
Nearest neighbors. Yes.
And yeah, so now, okay, so now we get a probability distribution px and
Okay.
into 1 minus phi x to the power n, which is the probability distribution of p minima. And so, and you know, one thing which beautifully comes up is suppose you have like, yeah, again, you have a 2D distribution
Uh,
of random variables and you chose minimum
yeah.
based on a particular criteria that the eight neighboring pixels would be higher than that. That means on an average, you'll get one minima per 9 pixels. You're choosing you're choosing,
Okay.
when you're selecting the minimas, so on average from that whole image, the the sample of those minima pixels will be 1/9 of the total number of pixels.
All right. Okay.
Uh, so that is also shown by the normalization constant, which
Right.
beautifully comes out by, I mean, if you do, if you go like analytically, then the normalization constant for this particular case will come out to be 9. This is 1 plus and 1 plus 8. 8 is the nearest neighbor,
Or it's not. Yeah.
number of nearest neighbor.
Yeah. Little n is
So basically, this is the normal. Yeah. So basically, yeah.
oh,
So intuition matches what the equation is, the analytical equation is. And if we, so yeah, so this is just what, intuitively came out. So but to test this, we did a simple test. Basically, we took a 2D array filled with Gaussian random variables.
uh-huh.
And you can go to the figure 1.
Yeah. Let's take a look at this in action. Okay. Here we go.
Yeah. Yeah.
Okay.
Figure 1.
I think we have a little bandwidth flag.
Yeah. So if you look at panel A,
Mm-hmm.
yeah.
Is that showing up on your screen?
Okay. So if you look at panel A, yeah, it is showing up. Yeah.
All good.
So if you look at panel A,
Mm-hmm.
so
Yes.
I've marked the minima pixels based on this particular criteria with this
Yes.
cyan dots.
Yes.
Yeah. So these pixels, when put in histogram compared to the histogram of whole 2D array, is shown in the
Yeah.
panel B,
Yes.
and it is overplotted with the parent normal distribution in black,
Yeah.
and the analytic minima distribution in
Okay.
cyan.
Yes.
Yeah. So basically, yeah. So yeah. So the analysis matches the test. What can I say more here? Yeah. So basically, yeah. So we get a form of minima distribution,
Okay.
and now we can say that if I just choose minima pixels, then, and if I take a mean of that, then and if I'm saying, okay, this mean should match the mean of probability, the actual parent probability distribution, it is wrong. It will be underestimated, but it turns out that it is related. It is related by what? It is related with the parent distribution.
Okay.
The mean of the minima distribution is related to the mean of parent distribution
Sure.
by a constant factor,
Cool.
which is the constant factor
Yes.
into sigma, which is
Okay.
the standard deviation of the parent distribution. And there we come to the third panel, panel C. The
Mm-hmm.
mean shift. What I'm calling mean shift is the mean of parent distribution minus mean of minima distribution.
Yes.
And sigma minima is basically the
I'm with you.
standard deviation of
Okay.
minima distribution. And they are
Okay.
linearly related to the standard deviation of
Mhm.
parent distribution. And if I just, so of course, I can directly take the minimas. And yeah, so basically these are related to the standard deviation, they're linearly related to each other.
Yes.
The
Mm-hmm.
mean shift and the sigma minima are linearly related to each other.
Mm-hmm.
And that relation is shown in the panel D.
Very cool.
Yeah.
Very
So,
okay.
so yeah.
Mhm.
So, but this relation, this mean shift versus this y is equal to mx rule, this m will be different for different type of distribution. Suppose you take a flat distribution, or you take a log normal distribution, or
Yeah.
any different continuous probability distribution.
Yes.
This will be different, but for that particular probability distribution, it will be the same.
Okay. I'm with you.
I mean, yeah.
Makes sense.
So, yeah.
Mhm.
So for Gaussian, it is this value 2.496. For others, it will be different.
yes.
but those particular values will be the same. Well, and this is what came out analytically also, and we tested it also. But yeah, but in the paper, I've only shown it for Gaussian.
Very nice. Very nice. Okay.
So yeah, we can go below. And for Gaussian, I have solved it for yeah, for Gaussian, I've also like solved it analytically, this value 2.496. I
Mm.
mean, this is from fitting. This is from tests that the value that we observe from tests. Yeah. So, but analytically also, if you go to yeah 2.2, I think yeah
Mm-hmm. Mm-hmm.
2.2, and you will see for Gaussian, I have solved it, and it comes out
Yes.
as a like in a final form. I mean, yeah, there would be yeah for a Gaussian distribution you can see from equation 13 and onwards. Like you can substitute and all, and
Perfect.
later you can get that particular value. So yeah, so here we have basically related the mean of minima distribution with the
Okay.
mean of parent distribution and sigma of parent distribution. So if you just sample the minima pixels, you can actually recreate the parent distribution from minimum
Pick it
pixels. That
up.
is the
Yes.
whole takeaway here. I'm
Yes.
sorry if I
No.
strayed.
There's 2.496. There's our 2.496 right there. And
Yeah,
there it is
yeah,
for Gaussian. And then we also do it for a Poisson.
yeah,
Do, do, do,
yeah. So
do.
yeah.
Okay.
One thing about a Poissonian is, yeah, because our photon counting is a Poissonian process, so we have to look for Poissonian process.
Uh-huh.
Like we have to do it, we have to calculate the same things for Poissonian. But the problem with Poissonian is that it is discrete.
Yes.
Discrete is hard to solve analytically.
Continues.
So I did the best thing that came to my mind is basically take
Yeah.
the test values from a Poissonian field,
Yes.
the 2D Poissonian field,
Yes.
and subtracted the analytic values from Gaussian
Okay.
and saw what was the difference
Okay.
for different lambdas.
Uh-huh.
And yeah, so modeled that particular thing, that particular remnant uh, with the power law. That is the third component there in equation 18.
Yes. Yes.
Yeah,
I'm
yeah,
with you. Hmm.
yeah. So yeah, you
Okay.
can see this particular thing in I think figure two.
Okay, very good. Let's go to figure two. Tests on that Poisson. So here we go on Poissons. Okay.
Yeah, yeah. So figure two, you can see this is like the first panel is a Poissonian field,
Yes.
and it's a low lambda Poissonian field. Like its lambda is 0.5.
Okay.
So the number of zeros is higher. One is bit lower, two is bit lower, and so
Right.
on. Like it goes like this. The distribution goes like this.
Okay.
This is just to show how a Poissonian field with like a low lambda would look like in general. That looks like your general noise basically
Okay.
in your astronomy image. But yeah, here if we go to panel B, so this is for uh, so what I did, I generated different Poissonian fields with
Okay.
different lambda values, calculated their mu minima because, okay, I'm not looking at the parent distribution itself
Right.
because I'm assuming that I won't know whatever the mean of that parent distribution is, so I cannot take all the pixels.
Right.
So I calculated their mu minima, and yeah, based on that mu minima, what my Gaussian like mu minima, Gaussian mu recovery would be. Based, if I assume that it is purely Gaussian, then I see that the constant factor, sorry, not the constant. This is the remnant factor
Yes.
is like from the the recovery value from this Poissonian minus what the recovery value of a Gaussian would have given me.
Yes.
Here we come to this particular
Hmm.
this remaining quantity, which is looking like a power law. So I
Yeah.
fitted a power law there.
We can
But
fit on that.
if we go to very low lambda values, which gives
Yeah.
me very low mu minima, you
Yes.
can see in the inset
Yes.
the actual C, goes down again, but this power law, of course, it is not a very good. The power law is not a very good estimate. So, but
Fit
this power
in
law can,
very
yeah,
small,
yeah,
right,
mu minimus. So this power law cannot estimate, like it does not give a good estimate there.
right.
Probably we can model it later
Okay.
in a better way.
Okay.
And it makes sense because your low lambda recovery it should be the remaining value should not be greater than the lambda itself, right? But your power law goes exponentially, like not exponentially, like
Right.
it goes steeper as lambda goes lower. So
Hmm.
your C cannot exceed your lambda. Basically, because it's that quantity minus an estimate, and that
Yeah.
estimate is always lower than that.
Right, right. So it can't be. Got it.
Yeah.
I'm with
So okay, so we thought okay, so
you.
we've got something. We've got this Gaussian relation of mu minima with yeah, and added
Correction.
a correction term for this, and
Yes.
let's see how well does it estimate. Like how well do we recover the lambda values in
Okay.
all these generated images? So we got like we put this relation there, and we tested it and compared it to just running the source extractor because source extractor is one widely used software. So we just wanted to see. So
Absolutely.
you can see,
Got
so
it.
it gives good recovery values.
Huh?
You can see at when lambda is high. But
Right.
as lambda goes down, you can see in the inset, like when lambda is almost less than one,
Uh,
because of this correction factor being overestimating the correction,
yes.
we see a very bad divergence. So yeah,
Right.
so for Poissonian, yeah,
Okay.
we
Okay.
win somewhere, we lose somewhere, and you can so yeah. So after that, one thing is okay in the regime that it works, in the lambda regime where it works.
Yes.
Let's try to populate with. We thought that let's try to populate it with point sources,
Okay.
and let's try if we like let's try to recover it. Let's try to recover the lambda from minimum pixels.
Yes.
Of course, we'll just look at the minima pixels in a field with Poissonians and point sources, and let's see if we can recover
Okay.
it better. So this is so yeah, we can go to the figure 3. So
Mm-hmm.
you can see it's a Poissonian field, populated with point sources,
Mm-hmm.
and the distribution of these point sources with like yeah. Like in the form of SNR, what is the magnitude of these point sources? It is just like we have just shown, like there are very noisy sources also, like below SNR 3, and like some a
Okay.
bit brighter sources like up to SNR 7. This was just to see how well it does in case of uh, faint sources, general faint
Ooh,
sources.
yeah, right. Okay.
And yeah,
Okay.
and we yeah, so basically there is now how the images are made is basically there is a background a noise point source,
Uh-huh.
and when we okay so yeah, so before this we have to go to section 3
Okay.
because section 3 is where I discuss this.
Yeah, that's where you discuss that. So let's go down to section 3.
Yeah, yeah.
Oops, I missed it there. And oh, here we are. We are in section 3.
Oh yeah, yeah, we are in section 3.
All good.
So
Okay.
again, one problem in doing this, like estimating background in a noisy image with sources, is that your minimas don't care where they lie; they can
Sure.
lie on sources also. So
Okay.
we looped back to the problem that we
Started
came
with.
here started with.
Yeah.
And okay, okay. I thought, okay, let's try masking these sources
Okay.
the best of my ability. And how do I want to mask? I don't want to use source extractor because then why don't I use source extractor from the
Exactly.
very beginning? Yeah. So okay, so one we can come to like figure 4. I think that is the
Okay.
masking, source masking
Here we go. Source
algorithm
mean background recovery.
flowchart.
Okay,
Yeah.
here we go. Yeah, this is a nice plot.
So how I carry on with the source masking is I'll take the image, I smooth it a little bit, and and I'll identify maximas.
Yes.
And for maxima, like yeah, for reaching a maxima, like you take a steepest descent path,
Uh-huh. Yes.
like the method of steepest descent, and whatever pixels point towards this one particular maximas are segmented with that particular maxima. And that is the segmentation map that you see.
Got it.
The third image here.
Yeah.
Like these particular pixels,
Okay.
when started from those pixels, they go towards that particular maximum, so they're segmented with that particular maximum.
Got it.
And what I did is I created a like 2D histogram. This is joint plot.
Mm-hmm.
Basically, this is the maxima value
Mm-hmm.
and
Excellent.
area of that particular maxima segmentation.
Segmentation. Okay.
And
Mm.
the idea was, okay, the sources may have higher area than the maximas which rise up from noise,
Yes.
and they will have the maxima value higher than those noise peaks. The basically the maximas which rise from noise.
Okay.
So you can see there are outliers in both the axes.
Yes. Mm-hmm.
So I thought, okay, let's clear the outliers,
Okay.
just do a sigma clipping,
Okay.
and
Okay.
and remove those particular segmentation, and whatever segmentations we are left with, we'll do our analysis there.
Mm-hmm. Okay.
And
Yep.
so basically we are left with very less space. You can see here I did a very uh, very sharp cuts, I think.
Right. Right. Okay.
So yeah, but in the leftover segmentations, we can like do our this analysis, and we can go to figure 2C,
Okay.
figure 2 panel C, to see the results.
Okay. 2C. Here we go. 2C. 3C. 3C.
Yeah, yeah. So here, the test is how many sources can I put there till what source count I can get my lambda value uh, very correctly, like the background value very correctly from this particular minima relation,
Okay.
using this same uh, source segmentation, like source masking.
Uh-huh. Mm-hmm.
So here we tested it with source extractor, and so we populated with first 69 sources, 138 sources. Sorry, so the patch is some 300 cross 300
Yeah.
where
Something.
we test this, I
Okay.
think.
Okay.
So yeah, so first very few amount of sources,
Mm-hmm.
uh,
Hmm. Interesting.
69. Then we increase the sources
Yeah.
quite a bit. I mean, this is per square arc minutes. I think this is two cross two arc minutes or so. So
Okay.
this would be double. So the source count would be double of this. Double, no, sorry, four times of this. So actual for at the actual source count in the whole patch that I tested. But yeah, and this scale length is based on the UVIT image that we had,
Okay.
because we're developing it for that. So yeah, so you can see up to a certain particular source count, which is I think 391.
Okay.
So the minimum method is able to get the lambda recovery within like 1 or 2% error.
Yeah.
But as the source count increases
Yes.
after that,
Yes.
source extractor does a much better job within like 10%, and we shoot up. Like we are not able to mask the sources.
Right.
That is what is happening there.
Right.
Because I provide a number somewhere in the paper that actually this particular number represents when the sources have covered more than half the area of the image.
Okay. Uh-huh. Okay.
So there's so we have reached a limitation here also in
Yes.
this particular case.
Mm-hmm.
So yeah, and First of all,
That'd be a
we did
crowded
not.
field. That'd be a very crowded
Uh,
field, right? So this is
yeah,
basically a statement about crowded fields.
yeah.
Yeah,
So there, you cannot use the conventional methods also, but you cannot use the minimum method also
either.
there.
It's crowded.
And also, if we need to mask sources before we calculate background,
Hmm.
that is, I don't know, that is a very, that is a circle that we are going in. Like we need to find sources. For that, we need background,
Yeah,
and to get a good
uh,
background, we need to mask sources.
it's
And
almost.
yeah, there are various limitations in directly using this minima method. But yeah, certainly with this particular exercise, we came up with a few conclusions from this. That
Okay.
okay, minimas. If we just look at minimas, then okay, they are biased, and we have to do some corrections there.
Yes.
And it can be yeah. So and it can be a good way to look at things, but not in very crowded spaces.
I'm with you.
And yeah, and also if you have some noises, suppose no, some artifacts also,
Oh,
it may also affect
sure.
the
Sure.
minimum method. The minimum method
Absolutely.
fail now.
Hmm.
So after this, we did yeah. So we went to the next phase,
Okay.
which is the original idea that we smooth the image. Let's smooth the image.
Okay.
Let's smooth your noisy image,
Yes.
and let's find out minimas there and put boxes there.
Okay.
But
Okay.
but again, if you're smoothing an image and you're finding out the minimas, you're putting the boxes there, what tells you that it is not biased? Because without smoothing also, we got a bias. The bias may be less, but there will be some bias because you are choosing minimas.
Right.
So
Right.
this particular action of choosing minimas gets you that bias,
Okay.
right? That is where the section 4 starts.
Uh-huh. Uh-huh. This is the right, crowded fields. Yes. Uh-huh. Exactly. Okay.
Yeah,
And here's our smoothed image and equation 20.
yeah.
And mm-hmm.
So yeah, so it was based on an intuition.
Okay.
So yeah, so let me go directly. This you can see this flow chart, right? Yeah.
Mhm.
So if you look at the first image, the topmost image,
Um,
uh,
I'm sorry, where you at?
it's a sorry, the topmost, yeah, the image one, yeah, here
Yes.
in this particular image.
Yes.
So
Okay.
you can see,
Uh-huh.
and this is a noisy image filled with those particular sources, the point sources.
Mhm.
And if I just smooth it and put minima, identify the minimas on that smooth image,
Uh-huh.
and then collect pixels at those locations in my original image,
Okay.
I I will put boxes everywhere wherever there is a minimum. And
Yes.
then your sampling location is directly dependent on just one kernel,
Okay.
and it may also be in a conjunction of three bright sources that you may see a minima there, and it will get your values up also. So I don't know. So I thought, okay, maybe if we can use two different kernels, a large kernel,
Right.
whose minimas will show me generally where there
Do
are
and work them.
like source-free regions in this particular image. And
Yeah.
around those minimas, you can see I2. This is the large kernel convolved image,
Uh-huh.
I2. If I choose minima there, so I'm assuming that this place is generally empty.
Yeah.
These places. So let me find let me start from here and convolve the first image I1 to with a smaller kernel
Okay.
G2.
Uh-huh.
And starting from the minimas in I2,
Yes.
I can get more sampling locations in I3.
Yes.
Okay, so now this and what this does is it serves a purpose that I am going away from very bright sources, and I'm looking at minimas in those regions.
Yes.
And now I can put boxes there. You can like come to the third. I think I can put boxes. You can see the
Yep.
boxes
Yep.
that I put there. I can sample pixels. I can do my statistics.
Cool.
But now, from like the minima statistics in section 2, we know that there might be just like the value that we saw, the 2.496 that was for Gaussian
That
and
would be
blue and
counted.
smooth images, that
Right.
particular 2.496 could be some other value here.
Could be.
And it doesn't matter because you're looking at minimas, you're selecting minimas. That action has put some constraint like on your selection, some bias on your selection,
Yes.
and the value would be lower than that. So let's try to find out what that value is.
Okay.
That was the idea here, and
Okay.
that is where we started testing. And we we came up with a few different tests
Okay. I'm with you.
to quantify how well does this method do.
Hmm.
And yeah, so we
Okay.
can go a little bit up maybe.
Yeah, sure.
No, sorry. Yeah, up, yeah,
Up.
up.
Hmm.
Page number 6, probably. Page number 6.
Page 6. Just wait for our background, our bandwidth.
Uh,
Where do you want to go?
sorry. I think sorry. Page number 7.
It's all
Starting
good.
of the page number 7.
It's all good.
Here you can see the equation 21.
Yes. Okay.
So if the equation 21 looks similar to that particular equation, right? That mu minus mu minima
Oh,
is
yeah,
equal
that
to
we saw that earlier.
2.496 sigma minimum. Yeah.
Yes.
But this would be
Equation
now,
7. Yeah.
yeah, yeah.
Okay.
So this would be now a function of this particular Gaussian kernel that we're smoothing the image with,
Okay.
and what length boxes we're putting.
Right.
This B. B
Yes.
is the box length,
Yes.
and G is and since we are using two different kernels, I discuss this in the appendix also, like what these two different kernels do, but it is
Uh-huh.
not specific. We just try to find out what that bias is using various fields, random fields,
Okay.
Gaussian and random fields,
Okay.
Gaussian random fields. I'm sorry. Yeah. And and if we find that if B is very large, this box length is very large,
Okay.
then, and large, by large, I don't mean like it should be like 50 or 60 pixels or something. Like
Okay.
it's more than 7 or 8 pixels.
Okay.
For our particular cases, this is again there in the appendix. You can see that the sigma minima is almost equal to sigma. Sigma minima is like the standard deviation of minima pixels, the sample pixels in minima,
Oh.
and sigma is basically the standard deviation of
Yeah.
parent distribution.
Okay.
This is what we observe from our tests, and we can change our equation 21 by like we can say that FGB.
Mm-hmm.
Oh, sorry, yeah. So this FGB
Yes.
can be like the sigma minima can also be sigma and can also be sigma minima. So we don't have to actually go for a separate separate equation to calculate sigma minimum. If we are using a large enough box, we can calculate sigma, which is almost equal to sigma minimum.
Okay.
The main thing is
Yes.
now we need to calculate the flat background that there is in this patch, and which will be calculated from this equation henceforth. And we get some values for this for a particular G value
Yes.
and a particular B value.
Yes.
We get
Do those boxes.
you can go a little bit below
Sure.
a particular test.
Okay. Process to empty. Locate empties. Test on random fields without sources. Try
Yeah,
to.
without sources. This
Mm-hmm.
one.
Okay.
See, so I have mentioned it here. Okay, so
Okay.
this okay, so we are using these two, right? Two kernels, big kernel and small kernel here.
Right.
So
Right.
these two are set to 15.3 pixels and 3.5 pixels FWH.
Here we go.
FWH, the kernels, the FWH of this kernels is 15.3 and 3.5 pixels.
Okay.
And I chose the sampling box size to be 7 pixels.
7 pixels.
And this gave me this particular value, 0.213 plus minus
Yeah.
0.002, and from this test.
Okay.
And from and this is, and you can see if I correct my yeah, so and after this in Poissonian, this is for Gaussian. I got
Yeah.
this relation from Gaussian random fields.
Yes.
Now I want to test this again, like we did in the section 2.
Okay.
I want to test this for Poissonian random fields,
Yes.
this particular empirical relation. For Poissonian random fields, I find that for this particular set of parameters, this G2, G1, and B,
Interesting.
okay, the and this sigma minima is not exactly equal to sigma, which is root lambda in case of Poissonian, but it
Yeah.
is sigma minima plus 0.1. It is
Uh-huh. Uh-huh.
near this value, and I correct
The
this, and
equation.
I show it,
Yeah.
and I show it in figure 6,
Figure 6.
the
Look at
the
that.
recoveries.
Figure 6. Let's zoom out a little bit. Get them both. Here we go. Okay.
Yeah.
Uh-huh. Uh-huh.
So
Good.
yeah, so you can see sigma recovered
Yeah.
versus lambda, so root lambda.
Yeah.
You know, it holds well when root lambda is somewhere above, I think,
Ah.
0.3,
Yeah. Somewhere around there.
and
Yeah.
and using this sigma minima, and like we're using this recovered sigma, basically
Yes.
root lambda, we
Uh-huh.
can we can do a lambda recovery in these particular images, and
Okay.
it holds well above lambda 0.1. So yeah, so
Yeah, because you're offsetting.
we have come like one step further from the previous thing, right? Because there the method did not do well before lambda 1,
Right.
and now at least with these particular like parameters in this particular method, we can go up to lambda 0.1.
Okay. Okay.
So now, like,
That's
yeah,
good.
you know, you can do like how many tests you want in empty images. The real thing shows up when you put sources there.
Right. Okay.
Yeah.
Okay.
So yeah. So here is a tests on simulated Poissonian fields with sources.
Uh-huh.
I did the same thing. Oh, okay. Yeah. So this particular test was done to quantify one more thing that can affect my lambda recovery,
All right.
which is the presence of sources itself.
Yes.
Okay. And what I did was I just generated a few like images with 500, 2000, and 4000
Yeah.
sources
Yep.
with
Inject.
with different background values, and using the same histogram that I showed in figure 2
Yes.
for
Okay.
the distribution of sources.
Mm-hmm.
Okay. And
This is a good
and
test.
if I
Okay.
yeah 0.7 to 7 SNR, this is
Mm-hmm.
and we define something which is known as source contamination of your background.
Okay.
So I'll take the noisy image, I'll do my analysis there. I'll put I'll smooth it. I'll put boxes,
Yes.
and then I know now where the boxes are put. Now I'll take these boxes and
Yes.
I'll put in the source field where there is no noise
Okay.
and there is no background. Just sources are there.
All
Like
right.
in this particular figure, the panel A is a noise-free source field, and B is noisy source field, which is there to emulate somewhat of a like observation. Yeah. So this is a very crowded. So this is
Got it.
an uncrowded field, and the
Right.
bottom two panels are like with the
It's much
crowded
more
field.
crowded. Okay.
Yeah,
I'm with you.
it's much more crowded. Yeah.
Mm-hmm. Mm-hmm.
So
Okay.
if I suppose I take the image on panel B,
Okay.
and I do my analysis that the analysis that is shown in the flowchart, and I
Yes.
put boxes there, and I just take those boxes and put exactly those boxes here in the source region.
Okay.
I can calculate what amount of flux my sources contribute
Yes.
to the background.
Uh-huh.
So that is what I call source. That is what I called like source contribution
Yes.
with this.
Yes.
And this source contribution actually can be compared with other method.
Sure.
Example, source extractor.
For example.
Basically, what you for source extractor, what I did was I take the mean I take the mean background, the value they give, and I take like the SNR, and I mask everything which is above this 3 sigma value.
Okay. That's a clip. Yep.
Uh, yeah. So so and whatever is remaining, like whatever pixels are remaining in this noise images, I can actually analyze the same pixels in the source field and see if if from source extractors method also I can get some source contribution to the
Yes.
background.
That's a good test. Mm-hmm.
I have, yeah. So you can see in the next figure, we compare
Yeah.
this source contribution term, this contamination fraction that I call it.
A little bit of
This
that.
is SC by lambda.
So this is in figure
Yeah.
contamination fractions. Yeah.
Yeah, contamination fraction. So this test that I came up with, it like, yeah, you can see
Okay.
in the x-axis, it goes from like lambda counts per pixel, like zero
Huh.
point 0.1 to 100, like above 10, I think it is the Gaussian regime. And contamination fraction in the y-axis, it's basically how many sources are there.
Right.
The top panel
Because
is the least
contamination fraction
crowded.
is SC over lambda. Okay. Mm-hmm.
Yeah.
Mm-hmm.
And you can see the minima sampling method, MS, which is denoted by MS here,
Mm-hmm.
does bit better in every case, almost in every case.
Very nice.
Yeah.
Very nice.
So even
Okay.
at this very crowded field, this
Yeah.
4,000 sources,
Uh-huh.
the minima method is almost order of magnitude better in the
Uh,
worst case
yeah,
scenario.
that is a log y-axis, yes.
Yeah.
Okay.
So this is the contamination fraction there. Yeah.
Mm-hmm.
So
Very good.
uh,
Very good.
so this was from this particular test.
Mm-hmm.
And next, we wanted to try this on an image which is almost as real but simulated, so that we know what background is there and what sources are there, what is the source distribution.
Okay.
So we wanted to do one final test here. And for that, I generated images with with AstroPy 2D modeling, SERSEC, the 2D SERSEC function there.
Oh yeah.
And I
Yeah, yeah.
took the
Yeah.
source values, the flux values from
Yeah.
Canucks catalog, the UVIT Good South catalog.
Okay.
The like flux radius, the 50% R effective radius, the
Yay.
basically the magnitudes, the everything is taken from there with a random placement of those sources
Yes.
and random ellipticity and random inclination.
I'm with you. Mm-hmm.
So in those yeah, and then again I made two different tests for a very uncrowded field and a very crowded field. You can see these are the generated image, and for that
Okay.
to emulate the low lambda and high lambda, you
Okay.
know,
Uh-huh. Uh-huh.
I gave it I gave it the background that we got in the catalog,
Yes.
and just multiplied the whole image with the T exposure and generated Poissonian noise with it.
Okay. All right.
So you can see this. So this the middle panel corresponds to a lambda of 0.348. When we multiply this particular image, this panel A with the calculated background
Uh-huh.
with the calculated background from the catalog. I mean, I put that flat background over it, these sources over it, and I just to emulate the exposure time effect.
Yes. Okay.
Exposure time effect. I just yeah, I generate Poissonian noise using NumPy, and we kind of simulated images here, UV simulated images
Mm-hmm.
of a almost
Mm-hmm.
uncrowded field and a crowded field. And
Uh-huh.
if we look at these images, you can see in the like low lambda,
Okay.
the noisy one, the middle two panels,
Yes.
you would consider that there are many less sources, but that is not the case. There are
Right.
many more sources, but to
A little more. Okay.
validate some of these sources, you'd have to do very careful background subtraction,
Yes. Yes.
right?
We know this.
And yeah, bright sources you won't care much, but
You're
for
going to get
very faint
those,
sources, you would,
which is the
yeah,
one you're
you would
after.
need a very, yeah. So we can go to the next figure.
Very nice. Very nice. Cool. Okay. Onwards, figure 10,
Yeah,
pixel histograms and
figure 10.
background recovery comparisons.
Yeah. So, so the first panel
Mm.
is of the more noisy images, that is
Uh,
at T exposure 3000, that is the noisy,
yes.
the panel B and C for the uncrowded and crowded field. I just
Uh,
placed
uh,
what the input background histogram would be by generating in a, like a empty empty array with just the Poissonian uh, Poisson random field at that particular lambda.
okay. I'm with you.
So
Okay.
this is so that is the gray histogram, the background, just the background.
Mm-hmm.
And if you see the presence of sources, it changes the overall histogram, the shape of the overall histogram a little bit. This is more. This is better shown in the panel B, where
The
I compare
uh,
at high T exposure. That is, you can
oh,
see the presence of a high number of sources have pushed the mode rightwards
yes. Mm-hmm.
of the whole image.
Yes.
Yes.
It's slid to
But
the
the background is still like
background of the
it's the same value. The
background.
background is still the same value.
Yes. Yeah.
But the presence of those many sources have pushed the mode of this image. So suppose you want to just run source extractor and be done with it. Source extractor's best estimate is the mode.
Okay.
So that is what it converges to every time. You
Okay.
can see in the panel A, because it is like the Poissonian is an like discrete, it's a discrete distribution. The background estimated in one of those discrete counts. That is basically corresponding to count one, and
Uh,
this is the counts are actually divided by T exposure.
okay.
So,
Okay.
but these peaks
Very cool.
are corresponding to count zero, count one, count two, and count three in the
Mm-hmm.
full integration time image. So you
Uh,
can see the source extractor's background in the case with 4,000 sources
yes.
is it's always near the mode
Yeah.
of these distributions of these images.
Yeah.
So if your image has less number of sources,
For
the
example.
mode is near the true background.
Okay.
If your image has a very large number of sources, then the mode is shifted, but that is the best value that you'll get.
You're gonna
But
get
with minima sampling, with this particular method,
yes.
we
And
are able to close in the true background. We are able to go close to the true background in both of
this
these
is
cases.
real.
Like these are two extreme cases. The first one is high noisy, low exposure time image. The
Uh-huh.
second one is in the Gaussian regime, but still crowding affects
Yes.
the background calculation. So
Very.
yeah, so that is one advantage that we see, and I have just written these values in table one,
Uh-huh.
so that you can see what is the percentage deviation
Very
in
nice.
all of these cases. Percentage deviation is basically the true background minus the estimated background by true background
Nice. Very
into
good.
100.
Yikes.
So yeah,
99. Yikes.
so yeah. I
Okay.
mean, these are tests with extreme cases. Source extractor is still a very fabulous thing.
It's a wonderful
It
thing.
can, yeah. But if you want to really go to the
Next
3
level.
SNR limit of your image, where there are true sources, but they may be overshadowed by a little bit overestimated background and all,
Yes.
you can use this method.
Very cool. Very cool.
Yeah. So this was our last thing, the last test that we did. And yeah. So
Beautiful.
basically, the discussions basically discuss these particular findings.
Uh-huh.
And
Very
we
cool.
have use this method in the catalog, in the this Good South UVIT catalog
Okay.
from our group. So this has been actually used in true images, and the background calculation is based on this particular method. But that paper came out before, so I mean, we actually ran more and more tests. We wanted to see if like it is as
Robust.
robust as we think. Yeah,
Exactly. Very cool. So,
we
yeah,
have discussed some, yes, application domains and all. Yeah, and
very good. Very cool. Is there do you have this as a notebook or a script or something that people can just
yeah.
download,
Actually,
right? Sex extractor. So how about this method?
yeah. So the whole recipe is in this paper.
Uh-huh.
I have the code. I actually want to actually want to make a module out of it,
Yes.
and like yeah, so that the people can just download it, install
Download it,
and
use it,
test.
go.
Yeah,
Mm-hmm.
yeah. So
Cool.
yeah, so some future that we see with this particular method
Okay.
is making a whole like module to detect sources with
Yeah,
the
a little more robust, let's
mm,
say.
minima based background and maxima based sources.
Right.
That is the like the idea which is basically currently there. But this needs a little bit more work done just to be converted to a module. The
Okay.
code is there. I have not uploaded it because I am also
It's
stuck
fine.
doing other
Um,
things. It's my last year of
Fine.
PhD.
Fine. Yeah. Oh,
Yeah,
so when
yeah,
well, I'll come back to that. Let's move out into
yeah,
the
sure.
main one before I get there. So
Yeah,
very cool. Okay. Pushback, I want to thank you so much for walking us through your very awesome new way to estimate background images. Very nice. Very cool.
thanks.
Um,
Uh,
yeah, and so we were talking a little bit about there about, maybe the software needs a little bit more polish or something along those lines before, you release it and things along those lines. And you
yeah.
mentioned you were in your last year of grad school. When do you graduate?
Um, so actually, I think my thesis will be submitted at the end of this year or maybe early next year.
Cool.
So,
Well, let me
so
be the
yeah,
first then to congratulate you, Dr. Pandy. Very nice work.
thanks. Thank you.
Yeah, very cool. Very good. And well, it'd be really exciting to see you develop this and polish it and get it out there so people can use it, right? Because you want people to
Yeah,
use it, right?
yeah,
So yeah, it'd be really cool to see this develop over the next year or so after on your PhDs.
yeah,
Very
yeah,
cool. Thank you.
yeah. Thank you. Thank you for giving me this opportunity to present this
Sure.
so that it reaches more people.
Cool. And that will do, everyone. And I hope this made your background astronomy day just a little bit better. And we will see you on the next one. Bye-bye.